This week we'll talk about stratospheric ozone depletion. Stratospheric ozone is a naturally occurring high concentration of oxygen molecules O3 in the upper atmosphere, um, which is unlike its harmful counterpart in the troposphere, which seals life on Earth. So its peak occurs around 22 kilometers above the surface, even though the actual number of molecules is tiny compared to oxygen and nitrogen. Despite being so thin, this layer absorbs most ultraviolet radiation, uh, preventing dangerous genetic damage at the surface level. So the figure here highlights its vertical distribution, showing that 90% of ozone lies in the stratosphere, where it serves as our protective barrier for the high for the um, ultraviolet rays or any other harmful rays that reaches the surface of the Earth. This is why its decline is a global concern. Ozone forms naturally in the stratosphere where when ultraviolet radiation splits oxygen molecules, allowing atoms to recombine into ozone. So this is an ongoing cycle, both absorbs harmful ultraviolet radiation and helps warm the stratosphere, as you can see in the figure first. Scientists measure total ozone in Dobson units with a global average of about 300 Dobson units. So the second figure illustrates that ozone is not most concentrated over the tropics, but is transported poleward, creating higher levels in cooler latitudes. In the 1970s, scientists linked human activity to ozone loss. Rowland and Molina showed that chlorofluorocarbons, once common gas used for refrigeration, reaches the stratosphere intact and releases chlorine when broken down by sunlight. So, as the figure shows, a single chlorine atom can destroy thousands of ozone molecules in a catalytic cycle, though its ban initially were resisted by the industry at first. Growing scientific evidences confirm that the use of chlorofluorocarbons are harmful and a threat to ozone. Several scientists highlighted how this human action disrupts atmospheric process. Chlorofluorocarbon was banned to use in the refrigeration process. Again, in the mid-1980s, scientists from British Antarctic Survey discovered a dramatic thinning of ozone over Antarctica, now called the ozone hole, defined as ozone levels falling below 220 Dobson unit. It appears each spring after the polar night as sunlight triggers rapid chlorine-driven loss. So the figure shows this sharp seasonal decline and its persistence over decades from 1970s to 2023. This finding confirmed Roland and Molina's warning about carbons and became a landmark example of human impact on atmosphere, stratosphere, uh, earning these two great scientists a Nobel Prize in 1995. The Antarctic ozone hole develops through a sequence of reactions tied to extreme polar conditions. In winter, reservoir gases such as hydrogen chloride, HCl, and chlorine nitrate, ClO, and O2 collect on polar stratospheric clouds and react to form molecular chlorine. When sunlight returns in the spring, this chlorine splits into reactive atoms that rapidly destroys ozone, as shown in the figure on the right. So the result is a sharp seasonal decline with ozone hole, depending quite quickly in September and October, highlighting the unique vulnerability of polar regions to atmospheric chemistry. Although similar chemical process occur in Arctic, ozone depletion there is generally less severe compared to Antarctic. So the difference lies in the temperature. As the figure shows here, Antarctic winters are colder and longer, allowing polar atmospheric clouds to persist for months, while Arctic conditions rarely reach such extremes. As a result, ozone holes in the Arctic are sporadic and smaller, though the strong depletion has occurred in years like 2019. This contrast highlights how geography and climate shape atmospheric process at two different poles of the Earth. The alarming evidence of ozone depletion spurred the 1987 Montreal Protocol, an unprecedented act of global cooperation. So initially aimed at reducing chlorofluorocarbons, CFCs. It was later strengthened through amendments in London and Copenhagen to speed up the phase outs and include the other ozone depleting substances in the protocol. So as the figure shows, chlorine levels begin to stabilize after the treaty, reflecting its impact. So remarkably, it became the first universally ratified UN treaty, and demonstrating uh, how science and policy can align to confront global environmental challenges. Um, Atmospheric chlorine has been declining since the mid 1990s, as shown in the figure, as a result of Montreal Protocol. Projections suggest that the ozone layer could return to 1980 levels between 2050 and 2070, though the Antarctic ozone hole will continue appearing annually because these chlorofluorocarbons linger longer in the atmosphere because of its chemical properties. This recovery is often hailed as one of the greatest environmental successes, offering valuable, though imperfect, kind of lesson for addressing global challenges like the challenges that we are facing facing in our lifetime, climate change. So, summary of the chapter. This chapter has highlighted the fundamental processes governing stratospheric ozone, its role in filtering harmful ultraviolet radiation, and the ways in which human activities have disrupted this balance. The Antarctic ozone hole stands as a clear evidence of large-scale atmospheric change, while the Montreal Protocol illustrates how international cooperation can mitigate such challenges. Current trends show gradual recovery of the ozone layer, though the persistence of ozone depleting substances ensure that this process will take decades. So today, recovery is underway, but will take again decades of time off, but it offers a key lessons for us to tackle broader challenges like climate change. Um, I think this is it for this week. Thank you for listening. Next week, we'll turn to another major environmental issue and explore its global implications.